بسم الله الرحمن الرحیم. عرض تبریک و تهنیت حلول ماه مبارک رمضان خدمت همه دانشجویان عزیز. جلسه دوم مجازی رو در خدمتتون فکر میکنم هستیم. انشالله که سالم و سلامت باشید و به اتفاق در ادامه جلسه دوم مجازی رو بریم. همونطور که میدونید جلسه قبلی و در مباحثی که به صورت آفلاین ضبط شد تا به الگوریتم گو بک اند رسیدیم، پنجره ها رو تعریف کردیم و یکی دو تا شکل رو هم تعریف کردیم خدمتتون. در مورد پنجره ارسال اشاره کردیم که پنجره ارسال 3 تا پارامتر داره، یه پارامتر SF، یه پارامتر SN و یه پارامتر اندازه پنجره که 2 به توان M هست. من تو این ادامه درس میخوام به این بپردازم که تو این شکل 1327 که چرا باید اندازه پنجره 2 به توان M منهای 1 باشه و اگر 2 به توان M منهای 1 نباشه چه مشکلی ایجاد میشه. اوکی. Hi everybody, happy Ramadan to you, and I wish you be safe and sound. Now, in the last sessions and previous sessions, we talk about some transport algorithms such as go back end, and I told you that send window has 3 parameters such as SF, SN, and window size to power m-1. Now I'm going to say you why we should follow the size of window to power m-1, and if we don't follow to power m-1, for example, we consider the send window size to power m, maybe we have some problem. In figure 13.27, this problem we can see this problem. We have 2 figures. In the left, do you hear me? Okay, you have my sound, my voice. You have my voice, student. It's clear. Okay. For example, in the left figure, in this figure, as you see, we have a send window. This window has 3 slots size, as you see, and the M value is 2. 2 power 2 minus 1 becomes 3. So the window size is 3, as you see, 0, 1, and 2, 3 slots under the window. For the first time, we have a request, so the sender sends the packet number 0 here, and Rn is 0. When receives packet 0, Rn becomes 1 and send back ACK1 to the sender. But because of noise, we lost the ACK1. Again, we have another request, so send packet number 1, and Rn is 1. When receives packet 1 becomes 2 and send back ACK2. But consider this situation that because of noise we lost packet ACK2. And finally another request, so sender sends packet number 2, Rn is 2 becomes 3 and send back ACK3, and again because of window we lost ACK3. In this time the window is full and we can send any other, the window is full and we can send any other packet because window is full. And the timer expires now. When timer expires, it means and didn't receive any acknowledgement at 1, 2, and 3. So senders imagine that their packets could not be received by receivers. So try to send to resend them. So send packet number 0. But because Rn is in receiver is 3, Rn receiver is 3, so drop packet number 0, and this is a correct action in the receiver because packet 0 received previously and no need to receive again, and so drop the packet. This is correctly discarded for packet number 0, packet number 1, and packet number 2. Here in this left figure, we don't have any problem because we obey, because we follow the rule, and the rule is send window size equals to power m minus 1. But in the right figure, as you see, the size of window increased by 1. In this figure, we select the send window size to power 2 or 4 slots we have under the window. We have a request. We have a request here, and so we send packet number 0, Rn is 0, becomes 1, send back ACK 1 because of noise, sender didn't receive this acknowledgement. Again, we have another request, and so send another request, send packet number 1, Rn is 1, when receives packet number 1 becomes 2, send back ACK2. Again, we have a missed packet ACK2 because of noise, for example, and packet another request, send packet 2, Rn is 2, becomes 3, send back ACK3, again because of noise. In a rare situation, a special situation, okay? And finally, the final request, so send packet number 3. Rn is 3, Rn becomes 0 because we are in module 2 power 2, we are in module 4. In module 4, the numbers are between 0 and up to 3, and again Rn becomes 0 and send back ACK 0. ACK 0 means I wanted packet number 0. Here the timer expires and sender didn't receive an acknowledgement, so try to resend all packet 0, 1, 2, and 3 to receiver again. And so send the copy of packet 0, to the receiver. But here, because Rn is 0, so accept packet 0. But we have a problem here. The packet 0 here, this packet 0 includes the old data that received by the receiver before, here. And this is a duplicate frame, no new data. Okay? But receiver received this packet previously, and receiver is waiting for packet 0 with new data. So accept packet 0 with old data as packet 0 with new data. In this case, and in this rare situation, receiver cannot find out that this packet 0 has old data, and receiver thinks that this packet 0 has new data, so it accepts packet 0, the new packet 0. And this is a wrong decision for the receiver because send window size cannot be followed by the receiver because the send window should be 3, and here in the right figure send window considered as 4. Okay. I explained this figure in the previous session, so I try to explain new figure. I try to explain this figure for you. Okay. In this figure, again, a good example for you. در این شکل دو مرتبه ما فرستنده و گیرنده رو داریم. سایز بسته 7، یعنی از 0 تا 6 که 7 اسلات رو شامل میشه سایز پنجره و ما توی ماژول 8 هستیم. چرا؟ چون شماره بسته ها از 0 تا 7 و M 3 هست. 2 به توان 3 8 منهای 1 7. Okay, in this figure the M value is 3, sequence number value is 3, and we are in module 8 2 power 3. And the window size is 2 power 3 minus 1 or 7. And we have slots in initial from 0 up to 6, 7 slots under the window here. 7 slots under the window here. Okay, we have a request for the initial SF equals Sn, but for the first request SF is 0 and Sn becomes 1. Packet 0 sent to the receiver. Rn is 0. Rn becomes 1 and send back ACK 1. And when receive this acknowledgement, we have a movement by 1 slot, and again SF and Sn equals becomes the same and 1. And we have another request, so send packet number 1. But consider we have a noise during the channel, and because of this noisy channel, we lost packet number 1. We lose this packet number 1, and we have a lost packet 1. Again, we have a request from the process, so send packet number 2. But because Rn is 1 in the previous situation and is waiting for packet number 1, so cannot accept packet number 2 because it's waiting for packet number 1. So send back ACK 1. ACK 1, it means I'm waiting for ACK 1, not waiting for packet number 2. We have another request here and send packet number 3. And because of the same reason, receiver doesn't accept packet number 3 and again emphasize its request. I'm waiting for packet number 1, not packet number 3. Okay? The timeouts, we have a timeout here, and so sender find out that their packet number 1, 2, and 3 cannot be received at the specific time, so try to resend packet number 1, 2, and 3. Send again packet number 1, Rn is 1, becomes 2, and send back ACK 2. Send packet number 2, Rn is 2, Rn becomes 3, send back ACK 3. And send, resend packet number 3, Rn is 3, Rn becomes 4, and send back ACK 4. By receiving ACK 2 here, sender drops the copy of packet number 1. By receiving packet number 2, ACK 3 drops packet number 2, and we have a movement. And by receiving ACK4, we drop a copy of packet 3, and we have another movement. So in this figure, we find out that acknowledgement are cumulative, and we find out that packets should be received in the receiver in order, and any out of order packet cannot be received by the receiver. Okay? You hear me good? You hear me good? My voice is good? Okay. In fact, we studied stop and wait and go back, and of course we can compare stop and wait with go back in. Stop and wait is a special case of go back in when we consider m is 1. When m is 1, in fact, stop and wait is a special case of go back in, and we can just have a window with size 1. A send window size is 1 in stop and wait. So stop and wait is a special case of go back in when with a value of m equals 1. Okay? We have another sliding window protocol in transport layer, and we call it selective repeat protocol. As you saw, we have some problem in go back in. Consider a situation that we have a noisy channel, like the previous example. When the channel is noisy, it means there is a probability that some packets cannot be received in order in the receiver. So at sender, we should resend all of them again. And this causes bandwidth wasting in network sources, wasting in CPU time, CPU processing, buffers, and all of them. So when our channel is noisy or error prone, in this case, it's better not to use go back in protocol, and selective repeat protocol is a good substitution for go back in. So go selective repeat, try to overcome the go back in problem. Okay, this is the philosophy, or this is the reason of using selective repeat. Again, we have some window, send window at sender, and receive window at receiver. But we have some differences between parameters and the behavior of operation of selective repeat protocol in comparison go back and protocol. Here again we have SF and SN, and we have send window. In receiver again we have receive window, but the size of receive window in the receiver is not 1, unlike go back and protocol. The size of window for send window and receive window, the size are the same. Here, the size of send window and receive window is 2 power minus 1. 2 power minus 1. M minus 1. 2 power M minus 1. M minus 1 is the power of 2. Okay? Is the power of 2. In the go back n, the send window size is 2 power M, then minus 1. Here, the send and receive window size is 2 power M minus 1. And 2 power M minus 1 approximately is the half of the 2 power M. 2 power M minus 1 is approximately the half of the 2 power M. So in this case, the send window size decreased by approximately half of send window in go back n. Okay? For example, here again we are in module 16 because the number of packets is between 0 up to 15. But if we are in go back n protocol, the send window size becomes 2 power 4 minus 1, 15. But here, for a selective repeat protocol, the size of window is 2 power M. M is 4. The 2 power 4 minus 1, 2 power 3. And the send window and receive window sizes are 2 power 3, 4 minus 1, or 2 power 3, or 8. So the send and receive window sizes are 8. For initial is between 0 up to 7. Okay, 7 slots we have under window, send window and receive window. Okay, again we have outstanding packets. Outstanding packets here are 0, 1, 2, 3. As you see, the color of some of them, for example, 0, 1, and 3 colors are red. Okay, the color for 0, 1, and 3 are red. It means these packet are outstanding packet, and they didn't acknowledge yet. But packet number 2 acknowledged already. Okay, SF is 0, SN is 4, and packets 4 up to 7 can be sent because they are not outstanding packet. So red packets are outstanding packet, not acknowledged. Gray color packet acknowledged, but they are out of order. And receive window. Again, for receive window, the size is like send window, and again 2 power 4 minus 1, 2 power 3, and 8. For example, in this figure from 3 up to 10, we have 8. We have 8 slots under the receive window. As you see, we have some gray color packet here. For example, packet number 3, 6, and 9. These are packets that received by the receiver, but they are out of order. They cannot be delivered to process. Should be buffered at the memory at transport layer at the receiver. When packet will be in order, then they can deliver to the process. So packets number 3, 5, 7, and 8, and 10, they cannot be received yet. Packet number 4 4, 6, and 9 received already, and but cannot be delivered to the process. Okay. We have timers again here. By sending packets, we start timers, and we have acknowledgement here. Another difference between go back N and selective repeat is about acknowledgement and types of acknowledgement. In go back N, as we saw, acknowledgement is cumulative. It means one acknowledgement can inform about all previous received packets. But in go selective repeats, acknowledgement it's not cumulative. Each acknowledgement just informs about that packet received in destination. Okay, not about previous ones. For example, we have an example here. Number entry means that receiver receives packet number 0, 1, and 2. But in selective repeat, acknowledgement number 3 is just about receiving packet number 3, okay, and does not say anything about other packets. This is another difference between selective repeat and go back N. But for a better understanding of the operation of selective repeat protocol, it's better to describe and explain finite state machine FSM for sender and receiver individually. Okay. No problem up to here? Can you understand? You understood me? Okay. Now it's better to study FSM for selective repeat protocol for sender. You are supposed to pay attention my explanation about this figure carefully, okay? Again, we in sender FSM for sender, we have two states, a ready and blocking state. In ready state, our window is not full and we can send more packets to the receiver. In blocking state, it means the window is full and we cannot send any more packets. So it's better to consider the situation. The first situation, we have a request that came from process. We have a request that came from process. By receiving this request, transport protocol at the sender side make a packet with sequence number equals SN, store a copy and send the packet, start a timer for this packet and increment SN by 1, and we have a new SN equals SN by 1. Then try to compare, try to find out that window is full or not. So check this formula, and if yes or true, it means we should immigrate to blocking state and we cannot send any more packet. If false, it means we are again in ready state and we can send more packet. Another situation for ready state is timeout. Timer expires. In this case, transport layer at the sender resend all unact packet in window, because under the window we have some act packet, we have some unact packet. So just send all unact packet again and reset the timer. Another situation in ready state, a corrupted ACK or an ACK about a non-outstanding packet arrives from receiver to the sender. In this case, we sender just discard this kind of ACK. Another situation, an error-free ACK arrived that acknowledges one of the outstanding packet. So in this case, mark the corresponding packet. If acknowledgement number equals SF, it means we can slide the window over all consecutive acknowledged packet. If there are outstanding packet, restart the timer, otherwise or else stop the timer. If we are in blocking state, and we have timeout, again we do like timeout at the ready state. If we are in blocking state and we have a corrupted ACK or an ACK outstanding packet arrive, again discard the packet. Okay, and if we are in blocking state and an error-free ACK arrived that acknowledge one of the outstanding packet, again mark the corresponding packet. If ACK number equals SF, slide the window over all consecutive acknowledged packet, and of course should again make a decision that window is full or not. If window is full, we come back to blocking state, and if window is not full, we immigrate from blocking state to ready state. Okay? This is explanation for sender, and this is another explanation for receiver. In receiver, we have just one state, and we call this state ready state. We have just one state, ready state. For example, consider an error-free packet with sequence number inside window arrived. An error-free packet with sequence number inside window arrived from sender. In this case, transport layer and selective repeat algorithm make a decision. If this packet is a duplicate packet, discard it. Else, store the packet. Send an ACK with acknowledgement number equals sequence number. If sequence number equals RN, deliver the packet to the process, and all consecutive previously arrived, of course, delivered to the process. And stored packets to application and slide window. Okay, a slide window. Otherwise, we don't have any movement for the window. Another case here. We receive a corrupted packet at the receiver and discard the packet. We just discard the packet. For another situation, receiver receives an error-free packet with sequence number outside window boundaries arrived. In this case, discard the packet, and send an acknowledgement with ACK number equals RN. These two FSMs individually for sender and receiver can explain us the behavior and operation of selective repeat algorithm. By studying details and overview these figures, we can have a good concept and understanding about selective repeat algorithm. So the first explanation for the algorithm is here. Okay. Can you tell me in this figure what's the value for M? What's the value for M? Please answer me. M is 3. M is 3. Yes, M is 3. Why? Because the number packet numbers are between 0 up to 7, and we are in module 8. So M should be 3. We are in module M, and M should be 3. And what's the send window size and receive window size? Send window and receive window is 2 power 3 minus 1, 2 power 3 minus 1, or 2 power 2, or 4. So send window and receive window sizes are 4. Okay, for initial 0, 1, 2, and 3 are slots under the window. Okay? Okay? M is 3 and send window and receive window sizes are 4. Okay. We have a request for the first time. So sender sends packet 0. Rn for initial is 0. When receives packet 0, Rn becomes 1. And we have a movement for receive window and send back ACK 0. By receiving ACK 0, we have a movement for send window, and again SF and SN becomes the same and 1, and we stop the timer. Here we have another request and send the packet number 1. But because of noisy channel, we have a lost packet number 1. We have another request. We send packet number 2, and Rn is 1. But here packet 2 can be stored in the buffer at the receiver and send back ACK2. ACK2 means I just received packet number 2. Okay? By receiving ACK2, we colored packet 2 under the window, and we don't have any movement for send window because packet number 1 cannot be acknowledged. Okay? Here, again, we have a request, so we send packet number 3. Rn is 1, but we can store and buffer packet number 3 because they are under the window, and send back ACK3. ACK3 means I receive packet number 3. And again, we colored packet number 3. We don't have any movement for send window because packet number 1 has not acknowledged yet. Okay, and finally here the timer expires. It means some packets should be resent. And the packet should be resent is packet number 1 because we don't have any acknowledgement for it up to now. So packet 1 resent, and when and of course the RN is 1. When destination receives packet number 1, RN is 1, RN becomes 4 because packet number 2 and 3 acknowledged before, and RN, we have a change for value of RN, and 0 becomes 4 and send back, and we have a movement 3 slots because we have 3 packets number 1, 2, 3 in order in the receiver, and these 3 packets can be delivered to the application, and we have a movement by 3, and send back ACK1. Send back ACK1 when this ACK1 receives by the sender, we have again a movement, 3 slots movement we have under the window, and window can move 3 slots, and SF and SN becomes 4. We stop the timer. Okay, understood? Okay. Again, if we don't follow the window size, maybe we have a problem in a rare, in a unexpected, in a special case. In a special case, maybe we have some problem if we don't follow the window size. We have 2 figures here, left figure and right figure. In the left figure, we don't have any problem because we suppose send window and receive window to power n-1. But in right figure, we have problems because we don't follow the send and receive window. And at first, I explained you the left figure. Okay. I ask you, what is the value for M here? What is the value for M here? Please answer me. Of course. Ahmad Abdul Hassan, I appreciate you. M is 2. Why? Because we are in module 4. As you see, packet numbers are 0, 1, 2, and 3. So we are in module 4. In module 4, it means 2 power 2. Okay? So M is 2. And send window is 2 power 2 minus 1. 2 power 2 minus 1 means 2 power 1. 2 power 1 means 2. So the send window is 2. Okay? Send window is 2. And we have just 2 slots under the window, slots 0 and 1. We have a request. We send packet number 0. We color the packet number 0. SF is 0. SF becomes 1. We send packet number 0. RN is 0. When receives packet 0, RN becomes 1, and we have 1 movement. Send back ACK0, but because of noisy channel, we missed packet number 0. Again, we have a request. We send packet number 1. RN is 1. RN becomes 2. We have a movement for receive window. Send back ACK1, but for noisy channel, because of noisy channel, we loses packet we loses ACK1. Here, window is full. It means we cannot send more packets. If we have a request, we cannot send more packet because the window is full. Here, the timer expires and we didn't receive any acknowledgement from the receiver at the sender. So sender try to resend the copy of packet number 0 and 1. So send again packet number 0. But as you see, under the receive window, we have two number 2 and 3. It means receiver can just accept packet number 2 and 3 and cannot accept packet number 0. So packet number 0 should be discarded. And this is a good action and correct action because packet number 0, the old copy of packet number 0 has been accepted previously, and we don't need to have packet number 0 because we received it previously. We don't have any problem here. But for the figure at the right, yes, for the figure at the right, we have here the size of window is not 2 power m minus 1, is 2 power m. M is 2 to power 2 equals 4. Okay? Okay. The size of window is not 2 power m minus 1. The size of window should be 2, but we increase the size of window 1 slots, and the size of window in this figure is 3. Okay? More than 2. We don't follow the rule. We don't follow the rule, and the size of window should be 2, but we increase it by 1, and the size of window is 3. This is a rare situation. This figure tries to explain if we don't follow the rule, maybe we face with a problem. Okay? Maybe we face a problem if we don't follow the rule. Okay? So we have a request, send packet number 0, Rn is 0, becomes 1. We have a movement for receive window, send back ACK 0. But noisy channel causes ACK 0 lost, will be lost. Packet, we have another request, send packet number 1, Rn is 1, becomes 2. We have a movement in receiver window, send back ACK 1, but because of noise, we loses ACK 1. Again, we have another request, we send packet number 2, Rn is 2, so when receive packet 2 becomes 3, and receiver window has a movement by 1, send back ACK 2. Because of noise, we loses ACK 2 again. In this case, timer expires, we have a timeout, window is full. If we have any request, we cannot send more packet because the window is full. Okay, sender didn't receive any acknowledgement. ACK 0, 1, and 2. All of these ACK packets were missed. So try to send the copy of Windows 0. But as you see here, we have 3, 0, and 1 under the window. It means if a packet with sequence number 0 is received at the destination because 0 sequence number is under the receiver window can be accepted. So in this case, the packet 0 with all data can be accepted by receiver as a packet 0 with new data. Okay? Packet 0 with all data has been accepted already. We don't need packet 0 with all data. We need packet 0 with new data. But in this case, packet 0 includes all data. But receiver suppose that this is a packet 0 with new data. Why? Because 0 is under receiver window. And this is not a true action. This is this decision is we have a mistake here. Okay, we have a mistake here. Why? Because we don't follow the rule. Okay, because we don't follow the rule. So we should follow the rule. And finally, as you see, in the transport layer, always maybe we, at the same time, maybe we download or upload the files, okay? The data we download or upload. It means maybe we are transmitter, sender, maybe we are receiver at the same time. Up to here, we discussed all transport layer with one assumptions, and the assumptions is that one side is sender, one side is receiver. But in fact, one side can be receiver or sender simultaneously at the same time. In this case, we using the concept of piggybacking. Piggybacking is a concept. Okay, in this figure, we use the concept of piggybacking for go back and protocol. In piggybacking, we add another field to a packet. In piggybacking, we have one type of packet, just one type of packet. Each packet has 4 necessary fields. One field is sequence number, one field acknowledgement number, one field checksum, and one field packet. Checksum is used for detection, error detection. But we use a sequence number for all packet, an acknowledgement number for all packet. It means maybe we have data, so we send a data packet with sequence number, and at the same time, by using acknowledgement number, we can acknowledge the opposite side for the for its received packet. Okay, so with a packet that carries data, that includes data, we send our data to the opposite side, and of course at the same time we can inform the opposite side about its data that sent for us. In this case, this concept is called piggybacking. It means I insert my data in the packet, and of course I acknowledge the opposite side by using this data packet. So in this case, in each data packet, we another acknowledgement number. Okay, acknowledgement number is added to our previous packet. In our previous packet, we have sequence number and data. Here we have sequence number plus acknowledgement number. So one packet can has two role, one role carrying data, and at the same time another role is informing about the received data. Okay, this is the concept of piggybacking. Here, as you see, each site, for example, client site has two windows. One window for send, one window for receive. And server side again has two windows. One window for send and one window for receive. Okay, and as you see, both sides sends the same packet. Okay, the same packet. Okay, this is the concept of go back in. This is the concept of go back in. This is the concept of piggybacking. Okay, at this time, this chapter is over, complete, and you can solve the exercises. At the end of this chapter, I ask you to send me the solution for me for next week, because you can solve the problem. Okay, because you can solve the problem. Okay. We have some problem here. But we have a summary here. You can study the summary. I explain all of them in details for you. And we have some exercises. I ask you to solve these exercises, okay, in details for me and send back me all of them. We have some research activity, but no need to do research activity. Exercises is enough. Solving exercises is enough, and I ask you to solve when you read a question, come back to the part that explain that question. Try to read that part in details and then try to solve the problem. Okay, the questions are very simple, but need to study deeply, and inshallah for next week I will receive your solutions. Okay. Okay. How many persons are there in my class? 1, 2, 3, 4, 5, 6, 7, 8. Oh, 21 participants. 21 participants. It's a good class. It means all of my students participated in my class, and just maybe 2 or 3% were, yes, absent in my class. Yes, appreciate you. Please read the text, read the chapter 13 in details, and I hope that I can transfer the idea of this chapter to you well. Okay. I think by using the site, you can send me the solution. By using the site Darsa software, I think you can send me the solution. Okay. At this time, I will to buy with you. I will buy with you. Inshallah, care of yourself against any virus, and of course, pray for me and these مبارک رمضان انشاءالله. خب تا جلسه بعدی شما رو به خدای بزرگ میسپارم. مواظب خودتون باشید. انشاءالله به امید خدا در آینده نزدیک شما رو زیارت کنیم. خدا نگهدار. God protect you. خدا حافظ. خدا نگهدار.